Let's break down the core idea behind this paper, the DeepSeek-V3 technical report from DeepSeek AI. We'll walk through 4 engineering tricks that made a frontier-class model absurdly cheap to train. Start with the number that broke everyone's brain. DeepSeek-V3 is a 671 billion parameter model that trades blows with GPT-4o and Claude 3.5 Sonnet, the best closed models on the planet, and it was trained, start to finish, for about $5.5 million. For a model this size, that's roughly an order of magnitude below what you'd expect. And here's the part that keeps engineers up at night. Across the entire run, on 14.8 trillion tokens, they never hit a single unrecoverable loss spike. No rollbacks. It just trained. The backbone isn't exotic. It's 2 ideas from DeepSeek-V2, Multi-head Latent Attention, which crushes the memory cost of the KV cache, and DeepSeek MoE, a mixture of experts where only 37 billion of those parameters fire per token. But the backbone isn't why it's cheap. The cheapness comes from 4 engineering tricks stacked on top, and in this video we're going to rebuild all 4 from scratch. Balancing the experts with no loss function at all, predicting several tokens at once, training the whole thing in 8-bit floats, and hiding the network traffic completely underneath the math. Let's go. Quick tour of the backbone, because the tricks bolt onto it. Attention is multi-head latent attention, worth a full breakdown on its own, but the one-liner. Instead of caching a fat key-value vector per token, it caches a small compressed latent and rebuilds the rest on the fly, so long-context inference stops drowning in memory. The feed-forward layers are DeepSeek MoE, not one big dense network, but a crowd of small experts plus a couple of shared ones that always run. A router reads each token and wakes only a handful of specialists. 671 billion parameters live in the model, just 37 billion fire for any given token. Giant brain, small electricity bill. And that routing is where our first trick lives. Here's the failure mode built into every mixture of experts. The router learns which experts to trust, and left alone, it plays favorites hard. A few lucky experts get picked for almost every token. The rest sit idle, barely training, wasting the parameters you paid for. That's routing collapse. And it's not just wasteful. When your experts are scattered across dozens of GPUs, a few overloaded experts means a few overloaded GPUs, and everyone else stalls waiting on them. So your expensive cluster runs at a fraction of its speed. The textbook fix is an auxiliary loss. You add an extra penalty term that measures how lopsided the routing is and punishes imbalance, forcing the router to spread tokens more evenly. And it works, but it's a bully. That penalty is fighting the model's actual job, which is predicting the next token well. Every gradient step becomes a tug of war. Language quality pulling one way, the balance penalty pulling the other. Turn the penalty up and load evens out, but quality quietly erodes. Turn it down and quality recovers, but the experts collapse again. You're stuck trading one against the other. The whole game is, can we get balance without paying that tax? DeepSeek's answer is elegant because it refuses to touch the loss function at all. Give every expert one extra number, a bias, BI, and here's the surgical part. You add that bias to the affinity score only when deciding who gets selected. Top K routing now picks experts by score plus bias, SIT plus BI. But this is the whole trick. The gate weight that actually multiplies the expert's output still uses the raw, original affinity, untouched. The bias steers who gets chosen. It never distorts how much their answer counts. 0 fingerprints on the model's math. So how do you set the biases? Not with gradients, with a thermostat. After every step, you check how many tokens each expert got. Overloaded? Nudge its bias down by a tiny amount, gamma. Starved? Nudge it up by gamma. Written out, BI becomes BI minus gamma times the sign of load minus target. Just the sign, plus or minus 1, never a gradient. An overloaded expert slowly turns less attractive. A starving one turns more attractive, until a token that would have been ignored crosses the line and lands back in its top K. And because it's a side control loop, not a loss term, it never pulls against next token prediction. Balance and quality stop fighting. The tax is just gone. The paper stakes the claim in a single line. Trick 2. Multi-token prediction. A normal language model is trained on one thin instruction. Given everything so far, predict the very next token. One token of supervision per position. That's a surprisingly sparse signal. The model sees a whole context and only ever gets graded on the single next word. DeepSeek-V3 densifies it. Alongside the main next token head, it bolts on a small chain of extra modules, and each one predicts a token further into the future. Module 1 guesses token T plus 2, Module 2 guesses T plus 3, and so on. So now, at every single position in the sequence, the model isn't graded once. It's graded on the next several tokens at the same time. Same data, several times the supervision. And the crucial design choice is how these modules connect. They're sequential, not parallel. Each module is fed the hidden state of the module before it. So the prediction of token T plus 3 is conditioned on your best guess of T plus 2. The full causal chain stays intact. You're never cheating by predicting the future independently of the tokens in between. That richer, denser training signal is most of why MTP makes the base model measurably better. And then it pays a second dividend at inference, which is the next beat. Let's open up one MTP module because the wiring is clever. Every module shares the main model's embedding table and output head, so you're not paying for a whole new vocabulary projection per module, just one small transformer block each. To predict at depth K, the module glues together two things: the hidden state from the previous depth and the embedding of the actual future token you're aiming at. It runs those through its transformer block, and the shared head turns the result into a distribution over the token at position T plus K plus 1. Stack a few, and you've got a little pipeline forecasting several steps ahead, each step honestly conditioned on the last. Now the inference payoff. During training, these modules sharpen the main model. At generation, you repurpose them as a speculative decoder. Let the cheap MTP heads draft the next few tokens in one shot. Then let the main model verify them in parallel and keep the ones it agrees with. DeepSeek reports the second token guess is accepted around 85 to 90% of the time, roughly 1.8 tokens out per step instead of 1. Nearly double the decoding speed, free, from modules you trained anyway. Trick 3 is the one nobody dared ship at this scale. Train an 8-bit floating point. Normally you train these giants in 16 bits. DeepSeek-V3 runs the expensive matrix multiplies, the big GEMs, in FP8, 8 bits per number. That roughly halves memory and doubles throughput on the tensor cores. The catch is that 8 bits is a cruelly narrow window. In the E4M3 format, you get about 4 bits of exponent, tiny dynamic range. So numbers a bit too big saturate, and numbers a bit too small flush to 0. And real activations have outliers. One freakishly large value in a block. Pick one scale factor for that whole block, and the outlier forces the scale so high that every normal value underflows into noise. Naive FP8 quietly destroys your gradients. The fix has two parts. First, fine-grained scaling. Don't scale a giant tensor with a single number. Chop it into tiles and blocks of 128, each with its own scale, so every little neighborhood sits in FP8's sweet spot. Second, high-precision accumulation. The tensor cores multiply in 8 bits, but the running sums get promoted to full FP32 before adding, so rounding errors don't snowball. Master weights and optimizer state stay higher precision too. The payoff was a genuine first. FP8 training proven stable on a model this enormous. Let's make the outlier problem concrete, because it's the whole reason tiles exist. Say you're quantizing a block of values that mostly sit around 1, ordinary numbers, but a single entry is 500. To fit FP8, you multiply the block by a scale, so the biggest value lands near the top of the range. But that scale is set by the 500, and once you apply it, your ordinary values around 1 get divided down to about 0.002, and in FP8's coarse spacing, that rounds to 0. The outlier survived, everything else got erased. One bad apple, whole block ruined. Tile-wise scaling breaks the coupling. Instead of one scale for the block, cut it into small tiles, strips of 128, and each tile gets its own scale from its own local maximum. The tile with the outlier scales around 500, the COM tiles next door scale around 1, and keep all their precision. The damage is quarantined to the tile that actually had the giant. Then the second half, accumulation. A matrix multiplies some hundreds of these 8-bit products, and adding many tiny numbers in 8 bits bleeds precision fast. So the instant products leave the tensor core, they're accumulated in full FP32. Cheap where you can be, precise exactly where it counts. Trick 4 is pure systems engineering, and it's the quiet hero behind the cost number. When your experts are spread across 64 GPUs, every token has to be physically shipped to whichever GPUs hold its chosen experts, and the results shipped back. That's an all-to-all, everybody talking to everybody. And in cross-node MoE, it's brutal. The compute-to-communication ratio is roughly 1-to-1. So for every second of math, you'd spend a second just moving tokens across the network. Do that naively, and half your absurdly expensive cluster sits idle, waiting on the wire. There's a second ways too. Pipeline parallelism splits the layers across devices. Device 1 runs the early layers, device 2 the next, but at the start and end of each batch, the later devices twiddle their thumbs waiting for the earlier ones. Those idle gaps are pipeline bubbles. DualPipe attacks both. It feeds micro-batches in from both ends of the pipeline at once, 2 streams flowing in opposite directions, which fills the bubbles a one-directional pipeline leaves empty. And within each chunk, it overlaps the phases, while the GPU grinds through the attention and expert math for one micro-batch. The all-to-all traffic for another is flying across the network underneath it, hidden completely. Communication stops being a line on the clock. It disappears behind the compute, which is exactly what lets them scale experts across nodes almost for free. Add it all up, and the bill lands here. For tricks, one suspiciously cheap frontier model. Does it actually hold up on the benchmarks? Spoiler, it does. If watching a training bill get dismantled trick by trick is your idea of fun, like, subscribe, and send this to the friends still quoting $100 million training runs. A word on the iron, because the software tricks only pay off if the hardware's fed. DeepSeek-V3 trained on a cluster of 2048 H800 GPUs. NVLink inside each node, InfiniBand between nodes, with custom all-to-all kernels written to squeeze every drop of that bandwidth. They also went to war on memory. They recompute cheap things like RMS norm during the backward pass instead of storing them, keep an exponential moving average of the weights parked in CPU memory, and, notably, skip tensor parallelism entirely, which is usually mandatory at this scale but eats bandwidth. Stack the savings, and the whole run came in at 2.79 million GPU hours, start to finish, without a single rollback. What did it eat, and what happened after? Pre-training ran on 14.8 trillion tokens, a bigger, cleaner mix than V2, weighted toward math and code, plus a 2-stage stretch that pushes the context window out to 128,000 tokens. Then came post-training, supervised fine-tuning to teach it to follow instructions, and reinforcement learning to align it with what people actually want. And here's the fun bit. They distilled reasoning ability out of DeepSeek, R1, their long chain of thought model, and folded R1's step-by-step problem-solving habits into V3, while carefully keeping its answers from ballooning into rambling essays. A frontier-based model, then polished with its own siblings' reasoning. So does it deliver? On the benchmarks, DeepSeek-V3 came out as the strongest open base model of its moment, especially in math and code, where it posts state-of-the-art numbers among non-reasoning models and even edges past some closed systems on tests like Math 500. Its chat version goes toe-to-toe with GPT-4o and Claude 3.5 Sonnet across a spread of standard and open-ended benchmarks, genuinely closing the gap between open and closed models. And the whole thing cost about $5.5 million, a small fraction of what a comparable closed frontier run is rumored to burn. Frontier-class results, startup-sized budget. For the record, straight from the paper. Now, is any of this actually causal, or just correlation with a big budget? The paper runs the controlled experiments, and 2 of them matter. First, the load balancing showdown. Train the same model 2 ways. Once with the classic auxiliary loss, once with the auxiliary loss-free bias trick, and compare. The bias-based version doesn't just balance the experts as well, it also scores better on validation. That's the key result, and it's the whole thesis in one chart. The old method was paying a quality tax for its balance, and removing the tax gives you both. You genuinely don't have to choose. Second, multi-token prediction. Switch it off, and the benchmark scores drop across the board, on reasoning, on coding, on math. The denser training signal isn't cosmetic, it moves the numbers. They also confirm the modules can be thrown away at inference with zero cost to the main model, or kept around for the speculative decoding speedup. So each trick earns its seat for a different reason. The bias fixes a problem the old fix created, and MTP squeezes more model out of the same tokens. Not a pile of lucky hyperparameters. A set of choices that each pay their own way. Let's stack the whole recipe back up. Start with the backbone, multi-head latent attention to keep inference memory small, and a DeepSeek-V3 mixture where only a sliver of the experts fire per token. Keep those experts balanced not with a loss that fights your model, but with a per-expert bias nudge like a thermostat after every step, plus or minus a hair. So load evens out and quality never pays for it. Densify the training signal with multi-token prediction, extra sequential heads that each forecast a token further ahead, which sharpen the model and then double as a speculative decoder at inference. Cut the arithmetic cost in half by training in 8-bit floats, quarantining outliers with pertile scaling, and catching rounding with FP32 accumulation. And hide the network entirely with DualPipe, feeding the pipeline from both ends and overlapping the all-to-all traffic underneath the compute so no GPU sits idle. None of these is a silver bullet. It's a dozen careful engineering calls, each shaving off a slice of cost, stacked until frontier quality fits a few $1 million instead of a few hundred. That's the whole magic trick, and there wasn't any magic, just discipline. The one-line version. Balance the experts without a loss, predict several tokens per step, train in 8 bits, and hide the network under the math, and a frontier model suddenly costs a few $1 million instead of a few hundred. Which leaves the real question hanging. If a model this good can be trained for $5.5 million, where's the moat? The big labs treat the compute bill as the wall around their castle, but papers like this keep quietly showing the wall is mostly cleverness anyone can copy. That's my read. Tell me yours. Until next time.